So I'm going to go over them now. And so horizon, astronomical horizon, and also the sky. Why is the sky a sphere? Why is the horizon circular? There'll be a question about one of those for sure. If you want to answer something, you're welcome to it if you like. All right, so then next question. Okay, so the Earth, when it goes around the sun, it gets closer to the sun, it gets farther from the sun. It gets closer to the sun, it gets farther from the sun, right? What do we call the point that is closest to the sun?
Focus.
No. Sorry. Today is the 18th. Okay. It's called perihelion, right? Okay, so that's one of the basic things that you should know. It's called perihelion. Peri means closest. Helion means the farthest. What's the farthest point from the sun? It's called, Noah is going to say something. Noah, what is that called?
Helion.
Helion means the sun. So the farthest from the sun is Greek, but you have to know that anyways. It's called aphelion. Aphelion, AP, helion. That means farthest from the sun. All right, so at one point, it'd be the farthest from the sun. At what point it would be the closest to the sun? So the sun is over here. This guy is going to be closest to the sun, then he gets farthest from the sun, then he gets closest to the sun, and so on. One point is called perihelion, one point is called aphelion. What is the average distance between perihelion and aphelion? What is that called? It's the distance from the center of an ellipse to the edge of the ellipse.
The semi-major axis.
Semi-major axis. That's right, Mr. Farmer. You get a point for that. That's Mr. Farmer. Thank you, Mr. Farmer. That's right. So semi-major axis of a planet's orbit is the average distance between the planet and the sun. And Mr. Farmer, what do we call the Earth's average distance?
The astronomical unit.
Very good. That's right. I'll give you another point for that one. Thank you, Mr. Farmer. The astronomical unit is the average distance between the Earth and the sun, but semi-major axis of the Earth's orbit is also astronomical unit, or the average distance between the Earth and the sun is the average, astronomical unit. But now you can have Mars get closer to the sun and farthest from the sun. We just say that's the semi-major axis of Mars's orbit, but that's not the astronomical unit. It's only the Earth's semi-major axis that is the astronomical unit. Okay. All right, next question. Why do objects rise in the east and set in the west?
The way the Earth
Because
rotates.
I'm sorry, Eva. Eva was going to say?
The way the direction that the Earth rotates.
Yeah. Which direction is the Earth rotate?
Counterclockwise.
Is it from west towards the east or east towards the west? If it rises, everything rises in the east, right? Remember? I'm sorry? Think about it. Just figure it out right now. Everything is rising in the east, right? So you have to, if something is rising over here, I got to turn towards it until I see it, right? So which direction am I moving to see it rise in the east?
West towards east.
From west to east. That's right. There you go. Eva figured it out. Excellent, Eva. Thank you. Eva's last name is DiCaro. Thank you, Eva. Great. Okay, now let's get to the latitude and how high above the horizon North Celestial Pole is and South Celestial Pole is and all that. All right. So I see North Celestial Pole 10 degrees above my horizon. What is my latitude?
10
10
degrees
degrees.
north.
10 degrees north is correct.
no,
Linda, that's right. Linda gets the point. All right, so I see astronomical horizon has North celestial pole, 0 degrees above the horizon. What's my latitude?
0 at the equator.
0, I'm at the equator. Now, Linda, if I look at the south horizon, would I see south celestial pole if I go on top of a mountain?
At the equator,
At
yes,
the
you will see
equator.
both.
That's
If
right.
you
see-
go very
Okay, very
high.
good. Thank you. Now, I have a question that I know Linda knows because she already asked me that question. I already answered it. I moved to 10 degrees north. How far below my southern horizon is south celestial pole?
80 degrees south.
Linda, how many degrees below my horizon is south celestial pole?
If you're at 10,
Uh-huh.
South Celestial Pole is 100 degrees. No. How many degrees below?
Okay, let's start again. I'm at the equator. Yeah.
Oh, you're at the equator.
I'm at the equator.
Mhm,
And I moved to 10 degrees north now.
mhm.
At the equator, they're both at 0 degrees. 0 degrees north celestial pole, 0 degrees south celestial pole. I go to
Mhm.
10 degrees north. North celestial pole rises 10 degrees above my horizon. How many
Yes.
degrees below my southern horizon is south celestial pole?
80 degrees north? No.
Isn't it
10.
10 degrees?
It's
below?
10 degrees. That's right, Mr. Farmer. Linda, you asked me that question on email, remember? So if one of them
Yeah.
is rising, the other one is going to go down, right? So if one of them rises 10 degrees above my horizon, the
Mhm.
other one goes below my horizon by 10 degrees, correct?
Thank you.
Yeah. And so I made a
Sorry.
video just for, no, sorry, you don't have to be sorry. I made a video just for that. It's about south celestial pole. So if I'm at 20 degrees north, north celestial pole is 20 degrees above my horizon. South celestial pole is 20 degrees below my horizon. So if I keep doing that, I can see one of them is rising, the other one is setting by the same amount. If one of them is going up, the other one is going down. One of them is going up, the other one is going down. All right. I made the video just for that. So there's videos at the end of chapter, I think it's chapter 4, I believe, to help you with the first quiz. It's also going to be on, same questions are going to be on the exam as well. All right. Let me ask you another question. We'll get it right finally. So let's see. All right, so I'm in London, 50 degrees north. How many degrees above my horizon is North Celestial Pole?
50 degrees north.
50 degrees. Very good, thank you. It's not, yeah, it's not 50 degrees north, it's 50 degrees above my horizon. Your latitude is 50 degrees north or 50 degrees south. But
Oh,
yeah, how many degrees above the horizon North Celestial Pole is? It's just an angle, like 10 degrees, 20 degrees, whatever. Now, I'm at 50 degrees again, same place. How many degrees of southern sky can I see?
50 degrees below.
South
40.
Celestial Pole is, okay, I guess I'm gonna show you guys. Okay, hold on, you guys. Give me a second.
One's 40 degrees south.
Right, I
Yeah.
can see 40 degrees of southern sky, you're right, but I think I better go over this one more time, you guys. I better go over this. Give me a second, let me get my program going. Right. Celestial sphere, okay. All right, let me see if I can share this with you now. All right, let me share this with you guys. I know we're gonna go overtime, but I don't care. All right, so we're looking at the northern horizon. And I'm gonna measure to see how many degrees above my horizon North Celestial Pole is. So here's North Celestial Pole. How many degrees above my horizon is it? Let me double check, let me see. It's 32 degrees above my horizon. From what latitude am I looking at it? What is my latitude if North Celestial Pole is 32 degrees above my horizon?
32
32
degrees.
North.
32 degrees, very good. So it's the same as your latitude. If your latitude is 32 degrees north, North Celestial Pole will be 32 degrees above your horizon. That's it. If I change my latitude to 40 degrees, look what happens, 40 degrees. It goes 40 degrees above my horizon. So it's the same as your latitude, right? 40 degrees. There it is, 40 degrees. Now, if I look south, if I look on the other horizon, I don't see the South Celestial Pole. It's below my horizon. I'm at 40 degrees north. How many degrees below my horizon is it? Well, it should be 40 degrees. I can see below my horizon here in this program. So I'm going to go horizon. See what's below my horizon. See-through horizon. Okay, there it is. It's 40 degrees below my horizon. So it's just as many degrees below my horizon in the south as North Celestial Pole is above my horizon in the north. That's the same exact thing. If I go to 0 degrees, what happens? If I go to 0 degrees, North Celestial Pole is 0 degrees above my horizon. South Celestial Pole now is also 0 degrees above my horizon. There's South Celestial Pole, 0 degrees above my horizon. All of this is on the little video. If you guys had watched it, you would know the answers to all of these questions. I suggest you guys watching those little videos. It'll take you less than 20 minutes. And then you can answer all the questions about all of this stuff. So if Captain Sparrow saw South Celestial Pole 10 degrees above his horizon, right? South Celestial Pole 10 degrees above his horizon, like that. What's his location? Where is Captain Sparrow?
10 degrees south.
10 degrees south. There you go. Now you have it. So if Captain Sparrow, South Celestial Pole, 40 degrees above his horizon, where is he?
40 degrees.
40 degrees south. There you go. Okay. So if he looked at the northern horizon, it'll be 40 degrees below his horizon. If I go here, North Celestial Pole now is going to be 40 degrees below his horizon. So at the equator, 0 degrees north or south, they're both 0. Then both of these guys are at the horizon, right? So it's the same as your latitude. Now we want to know how many degrees of southern sky you can see. I'm going to change my latitude to 40 degrees north. All right, it's 40 degrees north. How many degrees of southern sky can I see? So I look towards the south. How many degrees of southern sky can I see?
50 degrees.
50 degrees. Now you subtract. There you go. Now you subtract. Let me get the celestial equator up. There is my celestial equator. This blue line is the celestial equator. This is all in the southern sky. This is the southern horizon. I see this much of the southern sky. All I have to do is to take my, how many degrees above my horizon North Celestial Pole is. In this case, we are 40 degrees north. So North Celestial Pole is 40 degrees above my horizon. So that means that I can see 50 degrees of the southern sky because 90 minus 40 is equal to 50 degrees. All right. Anyways, there's videos just for that purpose that I made for you. Please watch them. All right, let's go to the next question. Okay. When we look at Santa's location, he's at 90 degrees north. How many degrees above his horizon will you see North Celestial Pole? 90 degrees, right? He's at 90 degrees north. That means he can see North Celestial Pole 90 degrees above his horizon. Now here's special because here nothing sets. If you look at the sky, everything is going above the horizon. Nothing ever sets. If you look at the west where things normally set, nothing is setting. They just go round and round. This blue line, remember that's a celestial equator. Celestial equator goes around Santa's horizon, all the way around Santa's horizon. But if I go to like, I don't know, like 80 degrees north, then some stars will start setting. Here, let's take a look at the west again. I'm going to go to 70 degrees north. Now, some of them are setting. Notice that everything is going parallel with the celestial equator, right? Like that. Everything goes parallel with the celestial equator. Everything. Now, let me get my horizon back.
Can I ask a question? Just
Yes, please.
so I'm sure I understand. So, if Santa can see at 90 degrees, you can see his NCP is 90 degrees above his horizon. Is the south celestial pole then 90 degrees below his horizon?
Exactly. Thank you. Very good. Excellent.
Okay.
Yes. Which means it's right below his foot. Right? All right.
Right.
Quickly. That's all right. No worries. Quick.
So, I still don't understand how latitude is the same as the distance, or
Because
the
maybe you haven't watched the video, my son. Let's take a look at the video. I'm just going to go there and you can see that the video is there. You just haven't taken time to look at it. Otherwise, you would have seen it, right? Get video. Get ready for the quiz 1. All right, so let's take a look. The celestial sphere, right? There's a celestial sphere video. If you had seen it, I shouldn't show it to you right now, but I'm showing it to you.
You're not sharing your screen.
Oh, not? Okay, give me a second. Un momento, please. Thank you for telling me, though. I appreciate that. Right, there we go. Okay, so this is at the end of chapter 4. You'll see it says videos to help you with the quiz. So here is the video I made you guys so you can see all the latitudes.
Even though the sun and the moon are vastly different in distance to the earth, to us on earth, it appears that they are both equally far away. In fact, the stars also appear to be equally far away, about the same distance as the sun and the moon. And this inability to tell distances when we look out forces us to see a celestial sphere, a sphere that surrounds us. Because we see equally far away in all directions, we're forced to see this sphere. In the middle of the sphere, we have the earth.
Okay, now you see a Santa here? North celestial pole is up here, is on top of his head, right? South celestial pole, just like Linda said, is right below his foot, just like that. Now, I made a video just so you guys can see the horizons and the celestial sphere, all the questions that I just asked you. Let's go a little
At
further.
the north pole of the earth, inside of the celestial sphere. So the celestial sphere surrounds the earth. And this is Santa at the north pole of the earth. When Santa looks around, he sees that the celestial equator is actually around his horizon. So that constitutes Santa's horizon. And since the stars are going round and round his horizon like this, around Santa's horizon, none of the stars at the North Pole ever set. They just go parallel with Santa's horizon. Now Santa moves to the equator of the earth. At this point, Santa sees celestial equator at his zenith, and he sees South Celestial Pole and North Celestial Pole if he just turns around. And so you can see North Celestial Pole and South Celestial Pole only from the equator of the earth if you go on top of a mountain. As the earth rotates, Santa will be able to see the other half of the sky as well. So Santa at the equator will have the chance to see the entire sky. The only observer that can see the entire sky is at the equator of the earth. This is me in San Diego, 32.5 degrees north. So Santa is at 90 degrees north latitude. This Santa is at 0 degrees latitude. I am at 32.5 degrees latitude. My horizon looks something like this. So how many degrees above my horizon is North Celestial Pole? Well, since I live in San Diego at 32.5 degrees north, we can say that the North Celestial Pole is about 32.5 degrees above the horizon. So we can say the altitude of North Celestial Pole or South Celestial Poles on Earth are the same as the observer's latitude. San Diego latitude is 32.5 degrees. Therefore, in San Diego, North Celestial Pole is 32.5 degrees above the horizon. Now we also see some of the southern sky. This is the southern sky. We see some of it. How much of it do we see? Well, all we have to do is to subtract our latitude from 90 degrees, and then we can find out how many degrees of southern sky is visible from San Diego. So in San Diego, 90 minus 32.5 gives us 57.5 degrees of the southern sky.
All right.
Okay.
So, yeah. Owen, did you have a question?
Yeah, I did watch that. I just for some reason since that then I lost how latitude was the same as like altitude or sorry. I'm having a hard time saying what I mean to say
That's
here.
okay. I understand what you're saying. No worries. All right. But so, yeah. So when you say you lost it, that means you forgot. That's
Yeah.
losing stuff in your head is called forgetting. So for the exam, you have to go over it again, right? So don't pretend like you're going to remember everything forever.
Yeah.
You got to get prepared again, right? As you get older, you forget faster. Don't worry. All right. So let me go over more. All right. I think all those questions are already answered that we're going to have on the exam anyways. Let me double check though. Go over everything. Okay, Eratosthenes. Make sure you guys know what Eratosthenes did, right? Eratosthenes. Does anybody know what Eratosthenes did?
He
Eratosthenes?
figured out that, I'm sorry, was somebody else speaking?
No, just you.
Oh. He figured out that our solar system is heliocentric as opposed to geocentric.
Eratosthenes?
Didn't he?
Eratosthenes. He's the guy from Luxor, Alexandria.
Yep. Mm-hmm. Right. He had
figured
his,
the size of the Earth.
oh, he figured out the site. Damn it. Okay. Sorry.
That's okay. Owen just said the problem, right? We forget. That's all right. We forget.
Oh, he was the one that did the shadow in the well thing.
That's right. That's him. He measured the distance between Alexandria and Eratosthenes. So make sure you know that one, you guys. All right. So who figured out the heliocentric theory and wrote a book about it and became the father of the heliocentric theory?
Copernicus.
Copernicus. That's right. Thank you, Owen. That's right. Owen's last name is Hamilton. Thank you, Mr. Hamilton. Hamilton. Okay, you get a point for that too. All right. That's right. All right, so astrology, when they developed astrology, why did they develop astrology? What was the necessity of developing astrology? What did they need to know? Why did they have to make a calendar for?
Agriculture.
That's right, Mr. Owen. That's correct, Mr. Hamilton. That's right. So it was because of agriculture that they didn't need to know all the dates. So they can plant their crops, harvest their crops on time and all that. Very good. That's correct, Amundo.
Professor, I have a quick question.
Yes, Tiara.
For Eratosthenes, I don't know how to say his name.
Eratosthenes.
Oh yeah. He measured the distance between Alexandria and what was the other place?
Luxor and Alexandria.
Okay, Luxor. Okay, thank you.
Yeah, and there was a difference in shadows of 7 degrees. So one shadow was long, and the other one doesn't even have a shadow in Luxor. So it's same place on the earth. We have a stick, or the well, whatever. We have a stick here. The shadow is different than the stick here. So the earth must be curved, right? That's why he figured out the size of the earth. He said, 7 degrees was 700 kilometers. He figured out the size of the earth. All right. Now, what about this Mr. Ptolemy guy? Mr. Ptolemy guy wrote a book. Does anybody know what his name of his book is? So Mr. Ptolemy's book, what is that about?
The Magnifica or something like that?
Magnificento? It's called,
Okay.
it's called Almagest. Almagest is
Oh,
Arabic, right?
majestic.
Majestic, that's right. There was a movie called Almagest. There's also a Majestic Theater too.
What was his name?
Ptolemy.
Ptolemy?
Ptolemy.
Okay, I thought you said Tony at first. I was a bit confused.
Ptolemy.
Thank you.
How do you spell Ptolemy? Anybody?
Is it
Ptolemy. Ptolemy. Ptolemy's is read Ptolemy. Ptolemy.
Like pterodactyl.
Really? Pterodactyl spelled with a P? I didn't know that. Thanks for telling me. Sheesh. All right.
I
So-
could be wrong.
Yeah, I don't know. Pterodactyl. I'm not into dinosaurs. So this Mr. Tycho Brahe. What did Mr. Tycho Brahe or Tycho Brahe do? Brahe is spelled B-R-A-H-E. Tycho Brahe. Tycho Brahe. What did he
But
do?
the
He built a
beer consumer?
observatory, right?
Was that the beer enthusiast?
That's the guy that got his, yeah, right. He got his nose chopped off and everything. Remember, he built an observatory on this island. He built his fantastic instruments. He observed Mars, but then he got in a fight with Kepler. He wouldn't give him all the data. Then he drank too much beer and he died. Then Kepler got all the information. And what did Kepler do with all that information? He figured out what? Figured out the orbits of all the planets in the solar system. All right, the same Mr. Ptolemy guy that we just talked about, that Mr. Ptolemy, he wrote a book called Almagest, but he also couldn't figure out the retrograde motion. He saw that the planets are moving in the sky like this, planet moving, 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 then planets stop, then planets go backwards, stop, then go forwards again. Why do planets go like that?
Because they are spinning around the sun, and we are too, but we spin at different rates.
That's called revolution, Owen, right?
Yeah.
So, yeah. So Mars revolves slower, we revolve faster. So every time you pass Mars, it appears to go backwards, right? Right. So now it appears to go backwards, but Ptolemy couldn't figure that out. So Ptolemy developed something. What is that something that he developed to figure out why Mars was going backwards?
The epicycle?
The epicycle, that's right. I'm sorry, you went away so fast I didn't get your last name. Look,
Hi, Larkham?
your last name is Marco?
Larkham with an L.
Larkham, that's right. Larkham. Thank you. That's right. That was Becky, right? Becca, sorry.
Yeah.
All right, very good. That's right. The epicycle. All right, let's get to this Mr. Galileo guy. Let's finish up the chapter 2 and chapter 4. So what about this Mr. Galileo guy? What did Mr. Galileo observe? He observed the rotation of the sun. He saw the sun is rotating. He noticed that when he looked at the Milky Way, he saw stars in the Milky Way. He saw that. He saw, his most important thing was the phases of Venus. because the phases of Venus, if the sun was the center of the solar system, it worked. That was fine. But if the Earth was the center of the solar system, then Venus should not have any phases. So that proved that the sun is the center of the solar system. He also saw the moons, craters, and mountains. What else did he do? I think that's about it, right? So what is it that he didn't do? He didn't see Mars. Mars is too small to see. He didn't. Was he the first one to see the moon? No. He was the first one to see the moon with a telescope. He didn't see it. Everybody has seen the moon already, right? Billions of people have seen the moon. Seeing the moon is not a big deal. Seeing the moon's craters and mountains, that's the big deal. Okay, let's finish this. Aristotle.
Professor,
Yes.
you said that what was that? Galileo, he figured out what with Venus?
Phases.
Oh, phases of Venus. Okay,
Phases.
thanks.
Yes. All right. So where does the sun rise on the first day of summer? First day of spring, which is 2 days from now. I think it's 2:30 in the afternoon. We say it's
I feel like when it sets, it feels like it sets at like, what do you call it? Like 4 AM or something, PM, 4 PM.
no, it sets at 6 p.m. But the question
Oh,
is, where is it? Where, not what time.
Oh. Uh. Like in the sky?
Correct. In the
Directly
sun,
overhead.
Earth. Hold on 1 second. So let's just make this 320. 320. So let's take a look. Where does the sun rise? On 320. Let's go back here. Let's take a look at the sunrise. Where do you think sun is rising?
Where are we in the world right now? Like in the world or
Take a look.
in the center?
What is that?
The east.
At the
Where does it
equator,
rise
at the
it?
celestial
the east.
equator.
That's right. It's on the celestial equator. And it's also rising exactly due east. Exactly due east. Exactly.
Due east, yeah.
That's why we
Okay.
say darn it. Yes, it's rising exactly due east. Now, let me go back again here. Jeez. God, I wish this program had a little faster speed here. Takes forever. Okay, so it's exactly due east. On the first day of spring, it rises exactly due east. That's why we have 12 hours a day, 12 hours a night. And then it sets where? Exactly due west. That's why we call it the equinox. Saturday is the first day of spring. Equinox means what? What does equinox mean?
Equal day and night.
Equal day, equal night. That's right. Equal day and night. That's right. That's exactly right. Now, how about the first day of fall? Same place, equinox again. What about the first day of summer? Let's be 620. 620. Let me back this down. Oh, look at that. Where are we? 70 degrees north. Let's make it 32 degrees north. Where do you think it's going to rise? Where is the sun rising?
north northeast.
Right. How much north of east is it rising?
More northeast than north.
How much?
North.
Why is it rising over here?
Because of the tilt of the earth.
Because of the tilt of the earth. Who said that? Was that you, Eva?
Yes, it was.
Okay, Eva gets another point. Eva's last name is... Okay, got you. That's right. It's because of the tilt of the earth. How about the first day of winter? That will be 1220. Anybody guess where it's going to rise?
Should be the opposite, right?
What does that mean?
So if it was northeast, maybe yeah, right there. Yeah.
So this is
east, southeast.
South of east. South of east. How many degrees south of east? 23.5 degrees south of east.
So south of east is how you refer to the space between east and southeast.
South of east is over here. This is southeast. It's between north and east. See, this is south. This is east. Anything south of east will be southeast. This is 45 degrees south of east. Because you saw SE doesn't mean only this is southeast. All of this is south of east. See?
Ah.
Yeah. This is all south of east. So this is east part of the sky. Anything north of east, this is north, will be northeast of the sky.
And you said 23 degrees?
Yeah, as the tilt of the earth is 23.5 degrees. Because of the tilt of the earth, we have the equinoxes. In fact, what is the yearly path of the sun called?
The ecliptic?
Ecliptic. That's right, Lourdes. That's right. And you didn't put your last name up there, eh? Okay. Sheesh, man, we're going to run out over time here. Let's hurry this up. All right, so Aristotle, let's make this the last question then. Aristotle. Aristotle, what did he do? He was the Alexander the Great's, what, tutor, right? So he was Alexander the Great's tutor, and he did what? The first person to prove that the earth is a sphere. Anyways, you guys always study for the exams. I understand and I appreciate the fact that you guys only study for the exams. So I'll be asking these questions on Monday. You guys will be all answering everything. Right now, you guys are just getting ready for it. All right. Okay. What is inertia according to Galileo? You can just write this question down. You can check it. It's all in your notes.
Mass?
Yeah. What do you say about inertia or this mass that we're talking about? Galileo said
it resists a change in vector.
Right. Can you put it in the way that everybody else understands?
It resists movement. Unless it's acted upon by a force.
Right. So it resists changing its motion. Resists changing its velocity. Velocity has speed with direction, right? Remember that?
It wants to continue going in the direction that it's already headed.
Right. So whatever's moving will continue that motion. If there's a force that changes that motion, okay, but otherwise it'll just keep on going forever. If you throw the ball, it should go forever. But on Earth, there's gravity, so it falls down. There's a friction between the ball and the air, so it drops down. But in space, it'll go on forever and ever and ever. Let's see. So we already talked about Mr. Tycho Brahe or Tycho Brahe. He's the one that bought the island, was drinking a lot of beer. He made instruments. He built observatories. He didn't have a telescope, though. He had no telescopes at all. Okay, is that it? I keep going back to Aristotle. So remember, the Aristotle, Alexander the Great's tutor, he figured out that the Earth is a sphere. How do you figure that out? What is it that gave it away?
Because he was in another.
Shadows?
I'm sorry, one more time?
You know, he took the same day was a shadow.
Shadow of what on what?
Was it the moon? It was
The Earth on the moon.
Yes.
On the moon, that's right. Was that you, Mr. Owen?
Yes.
Okay, thank you. Okay, all right. I think I'm done with those chapters. Let's get into chapter 3. Kepler and Mr. Kepler and then Mr. Newton. All right, let's see.
I have a question.
Yes, please.
About Tycho Brahe. How did he observe Mars without a telescope?
He watched it with just measuring the angles. He didn't really see Mars close up. He just watched the position of Mars.
Oh,
He gave that information, Andrew, to Kepler. Using that information, Kepler figured out the orbits of the planets, just by the position of Mars in the sky.
oh, thank you.
You're welcome. Now, if I could figure out how to position Mars in the sky. Okay, can you can still see this, right? Can you still? Okay,
Yeah.
so you see my hand here? Let's pretend this is Mars. Planets, including Mars, one day they're over here. The next day they're over here. Next day they're over here, like that. They keep moving towards the east, all right, like this, because they're orbiting the sun. But all of a sudden they stop and they go backwards, and then they stop and they keep going forwards. So they keep doing this. They moving like this, stop this way and go back this way. This is what he saw. He saw the motion of Mars amongst the background of all these stars here. That's what happened. All right. So let's do chapter 2 and 3 so we can get to telescopes. You guys, I spend about 20 hours making those little videos on telescopes. Please watch it because you get every single question correctly if you watch it. Every single one of those is in Canvas. There's 6 videos. All right, so don't forget the seasons in San Diego. Why do we have seasons in San Diego?
The tilt of the Earth.
The tilt of the Earth. That's right, Eva. Thank you. All right. I can see Eva has been given attention. All right. Question. Astronauts in space, Eva, do you remember why astronauts in space are weightless?
Because there's no pull from the mass of Earth, the gravitational pull from the mass of Earth.
Thank you. Anybody wants to correct Eva?
It's a very little amount of pull because of the distance. The distance between the two bodies being the astronaut and the Earth.
Anybody who wants to correct Eva and Mr. Owen?
Isn't it because they're in a constant state of falling around the Earth?
That's right, Trevor. Trevor, your last name is Shaw?
Yes.
Thank you, Mr. Shaw. That's correct, because it's a continuous falling towards the Earth. That's why. So as they orbit the Earth, right? As they orbit the Earth, they continuously fall towards the ground. That's a continuous falling towards the ground. All right, let's see if you guys can see this. So here's the Earth. There's the Earth. Astronauts are going around the Earth like this in orbit.
We
So-
can't see that.
Can't? Give me a second. I can see it. You guys can't see that? Really? So I'll put the other camera on. You can see that now? All right, so
Yes, thank you.
as the astronauts go around the Earth, you're welcome. Let's say there's the orbit of the astronauts around the Earth. They go this way and fall towards the Earth. They go this way and fall towards the Earth. They go this way and fall towards the Earth like that. That's a continuous free fall. And so if you jump off your chair right now, you are weightless. If you just jump off your chair, you'll be weightless. So because they're falling towards the Earth, like in Disneyland, we talked about it, remember? We're talking about Tower of Terror. So because of Tower of Terror, they're continuously free falling. What's the difference between speed and velocity, you guys? You need to know, by the way, speed, velocity, and acceleration, all 3 of them.
Velocity, direction.
I'm sorry, Lourdes was talking. I think Mr. Farmer started talking first. Mr. Farmer, you go ahead and finish your thought.
Isn't velocity a change in speed and direction?
Velocity is a change of speed and direction. I would say no. But Lourdes was going to add something. Lourdes, what were you going to say?
Just 1 sec. I'm looking at my notes, but let's see. Velocity has speed with direction.
Velocity is speed with direction. That's right. Velocity is speed with direction. So what is acceleration then, according to your notes?
Well, an acceleration would just be an increase in speed.
Change of velocity in time.
Oh.
Called acceleration, right? Change in velocity in time. All right, so let's do it. So I'm going at 50 miles per hour in the freeway, going north. I go in 1 second, I change my velocity to 60 miles per hour due north. What was my acceleration? I went from 50 miles per hour due north to 60 miles per hour due north in 1 second.
10.
What was my acceleration, Mina?
10.
Okay, no, not 10. 10 is not enough.
10 over 1 is not 10.
I'm sorry?
It was not 50 to 60.
Yes, but that's not acceleration. 10 is not an acceleration. You have to have units. What is the unit for that acceleration?
10 miles per second. 10 meter on. It was. What was your unit?
I was going 50 miles per hour due north. And then I went 60 miles per hour due north. And it took me 1 second to do that. What was my acceleration?
10 miles per second.
That'd be impossible. We can't. We don't have a car like that.
Right, we can't do that.
Is it 10 miles per hour per second?
That's correct. That is correct. That's right, Mr. Shaw. That is correct. All right, one more. I'm going at 100 miles an hour. In 1 second, I go 120 miles an hour. What was my acceleration?
$20 miles per
20
hour.
miles per hour, yeah, per second.
That's right, 20 miles per hour per second. To be completely correct, though, you should also say due north or due south or whatever, too. So you need direction as well. All right, very good. Parker, did you want to say something?
Oh, no, I just said the answer.
Okay. So now we go to racetrack. And the cars in racetrack are going in circles. They're not even changing speed. They're all going at 300 miles per hour. Wow, that's pretty fast. 300 miles per hour in a circle. Are they accelerating?
Yes.
Okay.
They always have to accelerate because 300 miles per hour in a straight line remains at no acceleration. But because they have to turn, there's more friction involved. So
it's not the friction, it's actually change of direction, right? Just like I just showed you, you can see that, right? You can see this.
Mm-hmm.
This is astronauts going around the Earth. You can also imagine that same picture is cars in a racetrack, right? So cars in a racetrack, they're changing their direction continuously. So let me go over it again. Acceleration is the change of velocity in time. What is velocity? Speed with direction. If you change your speed or your direction, you're accelerating. Even if you don't change your speed, just change your direction. You're accelerating, right? That's why it's an acceleration. Right.
Sorry, what would the acceleration rate be if the speed isn't changing, but just the direction? So like for instance,
You just have to know exactly how much direction you change. So your direction is actually got a little vector like Mr. Owen was talking about.
Okay.
Yeah. Like when you go into the freeway, right? As you go into the freeway, Noah, what happens to you? You have to go in a little circle, right? Why do they have to go in a circle to enter the freeways all the time? Why can't you just get in the freeway, you know? Why do you have to make you go in a circle? Because you can't go fast. You got to slow down. As you change your direction, you put a cup of coffee on top of your dashboard, it flies either this way or this way. And you can also feel it. You go, oh my God, like this or like this if you're driving, right? So they do that intentionally. They don't want you to go on the freeway fast. Otherwise, you get out of the freeway. Your car jumps out of the freeway. All right. Okay. Let's see the next question. Okay. Since we're doing chapter 3, let's talk about gravity a little bit. Now, let's say the moon's distance from the Earth changes. It becomes 4 times farther from the Earth. How much would its influence go down? Moon's gravitational influence decrease.
16 times?
Very good, Mina. Thank you. 16 times. That's right. So Mina gets a point too. That's right, Mina. So another question. If the moon gets to be 10 times farther from the Earth, how much would its gravitational influence decrease now?
100 times.
100 times. Very good, Eva. That's right. All right. Sheesh. Okay, so just remember, okay, now let's get to this, while we're at it, let's get to a question like that. Let me see exactly what I'm asking you guys on the exam, so I can give you the same exact, okay. We did this in class, but I'm gonna go over it anyways, since we're all reviewing. All right, so here, I wanna go away from the center of the Earth 10 times. So I move away from the Earth 10 times. I go way the heck away from the Earth. And I weigh 100 pounds. How much would I weigh if I go 10 times farther from the center of the Earth if I'm 100 pounds? I go 10 times farther.
Pounds.
I'm sorry, Mina, did you say something?
10 pounds?
10 pounds? No.
1 pound.
1 pound is correct, Mr. Farmer. Can you explain why the 1 pounds, please, so everybody else can hear you?
Because if you're 10 times as far and then you weigh 100, then
10 times 10 is
100.
100. So you have 1/100th the weight. If you weigh 100 pounds, now you weigh 1 pound. All right, let me give you another example. So we go, you're 200 pounds now. So I'm 200 pounds. I go 10 times farther. Now how much do I weigh?
2 pounds.
2 pounds, that's right. So let's see. If I go 6 times farther away from the Earth, how much would my weight drop? Lourdes says.
Wait, can you repeat the question one more time?
Yeah, I'm going 6 times farther from the Earth. How much would my weight change? How many times? 6 times farther means 36 times less weight. If I go 5 times farther, how much less would I weigh? 25 times less weight. If I go 8 times farther away from the Earth, how much would my weight fall?
64.
64 times.
64 times. So that's what you guys need to know. All right. Sheesh. Great. I think we'll have enough time by 2:15 to finish this. All right. So let's see. If something is, my distance is tripled, what does that mean? If my distance is tripled, it means 3 times farther. So if my distance from the Earth is tripled, then I'll be 9 times less weight. Triple means 3 times, right? Great. Okay, while we're at it, let's talk about this just real quick. Kepler's laws are going to be part of it, right? So Kepler's number 1 law, what does that tell you? Kepler's number 1 tells you what? Planets are going in elliptical orbits, and the position of the sun in the orbit is at the foci of the ellipse. So it's telling you 2 things. is telling you the position of the sun and also the shape of the orbit. It says they're going elliptical, and it tells you where the sun is. It's in the focus of the ellipse. That's the first law. Second law, basically, as far as you're concerned, will tell you, well, the planets get farther from the sun and closer to the sun, their speed changes. Do they go faster or slower? If they're closer to the sun, do planets go faster or slower?
Faster.
They go faster, that's right. If they go farther away from the sun, they go slower. Very good. Thank you, Eva. All right. Now, the third law is the one that I can give you a question. I'll give you an easy question. I won't give you a hard question. It says the time it takes a planet to go around the sun to the power of 2 is equal to its distance to the power of 3. All right. So let's say a planet is 4 astronomical units away from the sun. How long would this take this planet to go around the sun?
8 years.
Very good, Mr. Farmer. That's right. Do you want to tell us how you figured it out, please?
Did the square of was it the size of 4? And then
So you get the 4, right? You take it to the power of 3. So what's 4 times 4? 16. 16 times 4? 64. Now you get the square root of 64. The square root of 64 is 8. What number times itself is equal to 64? That's 8, right? All right. If a planet takes 8 years to go around the sun, how far away is this planet away from the sun?
For astronomical units?
Very good. That's right, Lourdes. So I'll either give you the distance, I ask you for a period, or I give you the period, I ask you for a distance. You can write this down. If I give you the period, you take the period to the power of 2, and then you get the cube root of it. That means what number times itself 3 times equals the number. So if I give you the period, you take the period to the power of 2. That means multiply times itself. And then you get the cube root of it. Cube root means what number times itself 3 times equals that number. So what's the cube root of 64? 4.
8.
4 times 4 times 4, 64. That's the cube root. What's the square root of 64, Noah?
8.
8. So, yeah. If I give you the distance, the average distance, then you take that to the power of 3, and then you get the square root of it. So if I give you the period, you take it to the power of 2, you get the cube root. If I give you the average distance, you take it to the power of 2, average distance, you take it to the power of 3, and then you get the square root of it. So if I said 4, you take 4 to the power of 3, that's 4 times 4 times 4, 64. Then you get the square root. Square root of 64 is 8. All right. Sheesh. Even if you didn't catch it, you can watch this video that we're making right now to get you ready for the exam. Also, those videos that I left you on your Canvas, they'll be really handy. Right. Sheesh. Okay. Let's see if there's anything else about this Kepler stuff. All right. Okay. So now I'm in space. All right. I'm weightless. I'm just weightless. I'm having a good time, you know, I'm weightless and all that. Now I have a question to ask you. So I have little pen in space. This is my little pen in space, all right? This is the third law of Newton's. I throw the pin, and the pin goes like this, like that, goes really fast. What would happen to me if I threw the pin? According to
You
the
go
theory.
back.
Okay, I go backwards, right? So I throw the pin goes really fast that way. And you said I go back? And how fast would I go back? As fast as the pin is going forward?
No, because you have more mass.
That's right, because I have more mass. The pen goes really fast that way because it has less mass. So I go back this way very slowly, right? Very, very, very slowly. So for every force, right? For every action, there is reaction equal and in the opposite direction, right? Okay, now, let's see.
You're saying that's in space.
Yeah, we're weightless. Yeah, we're weightless. Yeah. All right, now we're weightless again. I'm in space. And this time I have a toy truck and a 18-wheeler full of gas. Don't ask me how I get up to space. I did, okay? I have a flying saucer. And I'm gonna put the same force on the toy truck, a little tiny toy truck, as the 18-wheeler. Same force. They're weightless. Both of them are weightless. Would they accelerate the same amount? Which one will accelerate more, or is it the same amount? Owen says.
The lighter object would accelerate more.
Mm-hmm. Owen, you'd be correct. Now, why did you say that?
Because mass or inertia resists force.
That's right. So what you're saying then is that they're weightless, but they're not massless.
Yeah.
Okay. One way to remember this is this. You guys have seen people on the space station, right? If you could just, you know, touch the 18-wheeler, and 18-wheeler will fly off, then what is it to stop the space station from flying off? Like if you just touch the space station's wall, the space station will start tumbling, right? But it doesn't because it has mass. It's weightless, but it still has mass. Do you see? Otherwise, the space station will be in danger, right? If you're touching the space station only because it's weightless, it will start tumbling, but it doesn't, right? So you need to apply a lot of force to make the space station tumble, even though it's weightless. All right, sheesh. All right, what time is it? Sorry, 2. So we got 15 minutes left. Let me make sure. Let me make sure that I cover everything, though. All right. James Bond, right? You guys remember James Bond? He's driving around with that guy that has, you know, metal teeth, you know, the guy that was dangerous. He was like 7'4" or something. He's sitting in the driver's, James Bond is driving. The other guy's in the, you know, passenger seat. James Bond presses the button, the bad guy gets blown out. What happened to James Bond's car?
It's lighter?
Yeah, what happens to it?
It would have been pushed down. There was an ejection, right?
Right.
It goes faster.
What is that called, Linda? Going faster? That would
Acceleration.
accelerate. That's right. So his car will accelerate, right? If he goes faster, the car will accelerate. So if you got a truck full of watermelons and they fall on the freeway, your car will accelerate. And if you get all your family in your car, you can't accelerate. You've experienced this. You put 15 people in your car is just barely chugging along in the road because you have more mass in your car. So Kepler's number 1, 2, 3, Newton's law number 1, 2, 3. All right. I think we're just ready to finish the telescopes and get out of here. I can only wish you guys one fantastic thing, that you guys will get your $1,400 this weekend. I hope. Hope you guys are all, you know, qualify for it. But if you don't,
Is that only if you've already filed the taxes?
No, I just did it in 2019, so I'm good.
No, they'll just go off of your last tax year that was filed.
Right, that was 2020, so I did 2020, or I haven't done 2021. 2020 means 2019, right? Yeah, I'm good. I got my $1,400. I'm styling. Okay, one thing before I get to the telescopes, don't forget the leap years. Remember what a leap year is. Might have a question on the leap year as well. All right. Okay. Oh, one last question on gravity. So, using Newton's law number 2, why do we have multi-stage rockets? Rockets that have like 1, 2, 3 stages, you know, as they go up.
Because dropping them gets rid of mass.
Right.
And
Very good. Thank you.
mass
That's
is harder to move.
Right. Same reason why your car gets heavy, you can't accelerate. If you drop your mass, you finish your fuel, you drop that stage, the rocket will accelerate upward. That's right. Very good. Thank you, Owen. Well, Owen is going really good today, you guys. Mr. Hamilton, I gave you 3 points for today, but better yet, because of my old man memory, I will be able to get you a really good grade in this class, Owen. Somehow I have a good memory. I don't know. It just works out. Some people get older, they lose their memory. I'm gaining memory. Must be all the nun taking drugs. Okay, guys, let's get going. Let's get going on the telescope. There's only 10 questions on telescopes, and let's get out of here. Go have some fun. I'm starving. What's today? Not a Taco Tuesday. It's Thursday. Pizza Thursdays. All right. So, question. A refracting telescope. How many lenses is required to make a minimum visual refracting telescope?
2.
2, that's right. What kind of telescopes? What kind of telescopes? I'm getting tired. What kind of lenses do you need? What are those lenses called if you need 2 lenses?
On objective.
Objective?
And eye lenses.
I'm sorry, what was the second one?
Eye lenses? No.
Eyepiece. Yeah, that's the same thing.
Yeah.
Good enough, Mina. Yeah, I understand. Thank you. So you need an eyepiece and an objective. All right. So where does the light of the objective focus? What is that point called?
Focal point?
Focal point. Very good. Thank you. Yes. Okay. And Alondra says, I believe it applies to students, so you should expect it. We talking about money still? Sheesh. Alondra, you talking about money?
That was towards your comment on the stimulus check.
Students what? I'm sorry. Correct? I'm sorry, I'm missing it.
It was towards the comment you mentioned earlier about the stimulus check. It's unrelated.
Stimulus checks, yeah. Hopefully, I don't know, maybe you guys are making more money than $75,000 a year. I'm a poor guy, so, you know, I'm a teacher. We don't make any money. All right, so magnification of a telescope. I'll give you a focal length. You guys figure out the magnification. So I'll give you the focal length of the objective, focal length of the eyepiece. You guys get the magnification. I left like a 2-minute video on exactly how to do that. All right, so watch the video to see how you make the magnification.
And Professor, just to be clear, for the refracting telescope, those 2 lenses that you needed were objective and eyepiece, right?
Yeah.
Okay.
Eyepiece is the magnifier, right? And yeah, all you have to do is to watch those videos, man. I made it really, really quick videos, you know, because you can watch the long videos, but quick videos is something that you guys can deal with before the exam. Watch the quick videos, like a 2-minute video, you got the question on the exam right. All right. What is a light gathering of the objective? What does that mean? What does the light gathering mean? It means how much photons, how much light you can collect with the lens. or a mirror, right? So the bigger the diameter, the more you can collect, like a bucket. The bigger the bucket, the more you can collect, right? Light gathering. Light gathering. Yeah. Okay, it's chapter 6. Chapter 6. Can you guys see this? Chapter 6. Oh my God. Canvas is so slow. All right, so light gathering. I would watch every one of these little videos. This one is 2 minutes and 11 seconds. So what I said here is
Per bucket. So it seems that the area and the diameter of the buckets are all important in gathering the rain. Now, if we pretend that the rain now is photons of light, we can see the bigger the diameter of our objective telescope lens or mirror, the more light we can collect.
Right.
So if we compare a 4-inch lens versus a 2-inch lens, we can take the diameter of the 4 to the power of 2, divided by the diameter of a 2-inch lens to the power of 2. In this case, we're going to have 16 over 4, or 4 times more light gathering ability. So a 4-inch lens has 4 times the area of a 2-inch lens. Therefore, it can gather 4 times more light than a 2-inch lens.
There you have it. Right? Okay, so that's light gathering ability. How about a Newtonian telescope? What do you need to make a Newtonian telescope?
2 mirrors.
2 mirrors, that's right. You need what are those called? A primary mirror and a
secondary mirror.
That's right. Very good. Thank you. All right, just a couple of more questions and we're out of here, man. I'm getting really hungry now. Cassegrain telescope. So yeah, so a space telescope is a Cassegrain telescope, right? Cassegrain telescopes.
The focal point.
Yeah, right. They look like this. Let me stop this. Go to Cassegrain telescopes real fast. Cassegrain telescopes are reflective telescopes. So we go here.
This is an example of a Newtonian telescope. Every eye is different, so every observer it becomes very unruly. You're going to need a ladder like this to reach the eyepiece itself. Very, very inconvenient, astronomers.
So there's a
Cassegrain telescope is one design that has been favored by professional astronomers because the telescope is very compact and also has the focal point behind the primary mirror or the primary objective of the telescope. This makes it very convenient for installing big cameras and spectroscopes, so you can put a lot of weight behind here, whereas in a Newtonian, it makes the telescope out of balance because you put the weight on.
Okay, so yeah, I also made you one on seeing and also on mounts. So it tells you what seeing is and all that, right? So there'll be a question on Cassegrain telescopes. There'll be a question on light gathering, how much, so if you have like a 5-inch and a 10-inch telescope, how much more light you can collect, like that kind of a question. And then what kind of mount is the equatorial mount? What does the equatorial mount do? So that one has the rotation of the axis pointing at north celestial pole, and it rotates in the opposite direction of the Earth with the same speed. Let me